Hi, my name is Mark Bernhofen, and I'm a PhD student at the University of Leeds. Today I'm going to be giving a talk about some of the research I've been doing recently and how some of the findings can be relevant to the Water Hub countries. My talk today is going to be about using global datasets in flood exposure studies and some of the things you need to consider when using these global datasets. So I'll begin by clarifying where this research falls under the disaster risk definition. There are three aspects to having a complete understanding of flood risk. You need information about the hazard, so this would be the flood event itself. You also need information about the exposure, and this could be either people exposed or economic assets, such as buildings, infrastructure, or land. And finally, you need to know about the vulnerability of the people or assets exposed, and this would be how susceptible they are to damages or losses caused by the hazard. At the global scale, there are a number of data sets available for both flood hazard and exposure. They're less for vulnerability. The work I'll be covering today will focus on the hazard and exposure aspects of risk. Here's a little visualization of what I've just been talking about. You've got your flood extent, which is your hazard, and then you've got a map of identified settlements. If you intersect the two maps, those settlements that fall within the flood extent are exposed to the hazard. So what global data sets are there for flood hazard? Well, the last decade has seen the development of global river flood models. These models use globally available datasets and automated frameworks to map flood hazard globally. They're particularly useful in regions and basins that lack the data to develop local flood models. The usefulness of these models has led to multiple global flood models being developed by different universities, research groups, and private companies. Each model adopts a slightly different approach to modeling flood hazard globally. So what you get are models that operate at different resolutions using different input data sets and different hydrodynamics. Mark Trigg did a study a few years back comparing the output of 6 different global flood models in Africa. That study found between 30 and 40% agreement between the 6 models, so the models differed quite significantly. It also produced this nice graphic to the right here where you can visualize the levels of agreement between the models in Africa. You can actually download and work with the dataset shown in the figure here to the right. I'll share a link at the end of the presentation of where to download it. You can also download and work with the output of a lot of the global flood models. If you have any questions about using them and how to access them, either Mark Trigg or I would be happy to help you, so please contact us. So how about exposure? What global data sets are there to calculate exposure? So for the purpose of this talk, I'm going to be talking about people or population exposed. There are a number of different freely available global population data sets. And just like with the global flood models, there are a number of different methods for mapping population globally. A useful resource I've found when working with population data sets is PopGrid. The PopGrid is a website that lets you easily compare different population data sets. The image to the right is the interface on the PopGrid website that lets you compare the data sets. Here I'm comparing 4 different global population layers for Nigeria and the surrounding countries. So as you can see, when you use different population layers, the methods for mapping population vary significantly. If you're planning on using these data sets, I recommend checking out the website. I've posted the URL on the slide here. It's popgrid.org. And there's also a paper that dives into greater detail about the different methodologies for mapping population. So that's the Lake et al. Paper. I'll add the reference at the end of this presentation. So I've given you a brief summary of what global data sets are available for both flood hazard and global population. But as an end user wanting to use these data sets to calculate flood exposure, how do you decide which of these data sets to use? And what impact does your choice of data set have on your results? So that's what I'm exploring with this research. How do differences between global flood models and differences between population data sets affect flood exposure estimates? So I talked earlier about some of the differences between the global flood models, about how they use different input data sets, operate at different resolutions, and employ different hydrodynamics. Well, here I'm going to be exploring just one of the ways the global flood models are different, their river representation. The models have different river size thresholds for which they model flooding. These are expressed in upstream drainage area, so that's the area of the basin that drains into the river at a given point along the river. I've listed the names of 5 different global flood models and their drainage thresholds in this table here on this slide. And I'm going to be using Sri Lanka to help visualize what these different drainage thresholds mean in terms of rivers modeled. So all the global flood models model flooding on the largest rivers, those with an upstream drainage area of 5,000 kilometers squared or greater. But as you reduce the river size threshold and incorporate more rivers into the modeling framework, less of the global flood models are able to model flood hazard on these rivers. Currently, the most representative flood model models flooding on rivers with an upstream drainage area of 50 kilometers squared or greater. It would be interesting to explore what impact improved river representation beyond current global flood model levels would have. Say to include rivers down to an upstream drainage area of 10 kilometers squared. So I'm not going to dive into the methodology in this talk, but I'll leave this slide in for those of you who want to have a closer look. Essentially, we want a flood hazard map that is independent from the global flood models, and that explores only the differences between the models in terms of river representation. So what we use is what we call a river flood susceptibility map, which is a geomorphological approach which derives a river's susceptibility to flooding from the terrain alone. Here's what the river flood susceptibility map looks like for Sri Lanka, color-coded for the different river threshold ranges. To calculate exposure, I used 3 different population maps. The first, which you can see on the left of the slide here, for Sri Lanka, is Facebook's high-resolution settlement layer. This dataset was produced as a joint effort between Facebook and Columbia University and utilizes ultra-high-resolution commercial satellite data to identify individual settlements. Census data is then distributed across these identified settlements to produce population maps at 30 meters resolution. At the moment, only the population of 166 countries has been mapped, but they're working towards global coverage. The second population map, shown here in the center, was produced by the European Commission Joint Research Center and is called the Global Human Settlement Population Map. It uses Landsat imagery to identify built-up areas and settlements, and then distributes census data over these identified settlements. This population map is available globally at 250 meters resolution. The final population map shown on the right here is WorldPop, which is a dataset produced by the University of Southampton. And while the last 2 datasets I described identified settlements and then spread census data across these settlements, the WorldPop approach to population modeling is slightly different. It incorporates a number of different ancillary datasets such as roads, land cover, structures, and environmental data, and uses these to dynamically spread the population over an area. WorldPop is available globally at 90 meters resolution. So as you can see, the 3 population layers all employ different methods to mapping population. And you can see that for Sri Lanka, that although the total population is the same, the way that that population is spread across Sri Lanka is very different. Flood exposure was calculated by intersecting the river flood susceptibility map, which I showed a few slides back, and the different population layers. My research has more of a global focus, so I'll begin by summarizing some of the global results I found, and then I'll dive into the water hub countries specifically. Global exposure calculated using the most representative global flood model river threshold was calculated to be around 1.75 billion, whereas the global exposure using the least representative river threshold was around 0.75 billion. So the difference between these 2 figures is over double. And this difference was often more pronounced at the country level, and I think this emphasizes the importance of considering river representation when choosing which global flood model to use. We also found that over 220 million people potentially exposed to flooding are not currently modeled by any global flood model. So this is the portion of the bar chart in red here. So what about the population layers? Well, in the 166 countries where all 3 population datasets were available, I found that Facebook's high-resolution settlement layer predicted significantly less exposure than either the Global Human Settlement Population dataset or WorldPop. Now I'll look into the reasons for this in a few slides' time when I'm looking at the water hub countries specifically. And finally, I found that the differences in exposure as a result of using different population data sets were most pronounced on the smallest size of river. So if global flood models do improve river representation to include these smallest rivers, it is equally important that we have population data sets that are able to accurately map the exposure to these smallest rivers, as currently this is where there seems to be the greatest uncertainty. So here are the results for the water hub countries. As you can see, India is on a completely different scale, so we've had to put it on a separate axis. The greatest proportion of flood exposure in India comes from the drainage threshold range that is modeled only by the most representative global flood models. So that would be the orange section of the bar chart here. I think in India, the greatest benefit would be seen from using the most representative global flood model. If you look at Malaysia, say you were using a global flood model that only modeled the largest rivers, so that would be the dark green section of the bar chart. You'd be missing 90% of the rest of this exposed population. Another interesting thing to note about Malaysia is the exposure changes from using the different population data sets. So that's the length of the bar chart compared to one another. The exposure differences between the different population data sets are far less pronounced in Malaysia than in the other countries, and even the global figures that I shared on the previous slide. This suggests that these population data sets could be used interchangeably without having too many issues. In Colombia, the largest rivers are responsible for the most flood exposure. So again, the dark green section of the bar chart. But even so, if the other rivers were incorporated, twice as much exposed population would be represented. And finally, we've got Ethiopia. Ethiopia is an interesting case, as the choice of population data set for calculating exposure can have a bigger impact on exposure estimates than the degree of river representation. For the remainder of this presentation, I'm going to be looking at Ethiopia, and I'm going to explore why the different population data sets lead to such different exposure results, and some of the things to consider when using these population data sets in flood exposure studies. I'm going to be looking at 3 study basins in Ethiopia: Abai, Awash, and Rift Valley. I'll begin in Awash. Awash was split into smaller drainage basins. So these are level 8 hydro-atlas drainage basins for those of you interested. And for each drainage basin, I calculated the exposure disagreement between the population datasets. So basins that are blue have better agreement between the population datasets in terms of exposure, whereas basins that are red have higher disagreement. I'm going to explore a handful of these high disagreement basins across the 3 study regions in Ethiopia. Each will highlight a different way that the population datasets differ and why this leads to differences in exposure. The first high disagreement basin I'm going to look at is the one containing the city Addis Ababa. So you can see that 3 population datasets all capture the city of Addis Ababa. The flood extent is shown in pink on the maps. If you look on the graph on the left, you can see that Facebook's high-resolution settlement layer predicts the least flood exposure, followed by the global human settlement population dataset, and finally WorldPop predicts the most exposure. So I can identify 2 reasons for the levels of disagreement here. Firstly, if you look at Facebook's high-resolution settlement layer map, the map on the left here, the high-resolution settlement layer is able to identify settlements at the building level. This means that you can see within the city that where there is a flood extent, there are fewer buildings. The high-resolution settlement layer is able to better capture the population's avoidance of the flood hazard areas. When you compare this to the other 2 maps, they're not able to capture this. So I think this really comes down to the resolution of the different data sets. Now, the reason that WorldPop's exposure estimates are higher than the other 2 population data sets is also due to the way that WorldPop distributes population over a large area. So you can see there's a lot more purple in the WorldPop map there in the middle. This then undoubtedly results in higher exposure estimates, as say the large inundated area to the south of the city will result in more exposure for WorldPop than the other 2 datasets. Now let's look at one of the other study basins, Abai. Again, here we split Abai into smaller drainage basins and calculate the level of exposure disagreement within each of these smaller drainage basins. The first basin we're going to look at is this one in the southwest of Abai. So on the graph on the left here, you can see that WorldPop predicts far more flood exposure than either of the other 2 population datasets. And this really comes down to the method that WorldPop used for spreading population over a large area. So you can see Facebook's high-resolution settlement layer and the global human settlement population dataset. These two datasets identify settlements, and the settlements they've identified are outside the floodplain. WorldPop's method of spreading population over a large area is incorrectly predicting a lot of flood exposure within the floodplain. Now let's look at another high disagreement basin within a BI. This one to the west. So in this basin, you can see that the global human settlement population dataset predicts far more flood exposure than either of the two other population datasets. To shed some light on this, I think you need to zoom in to the north of this basin. I'm going to do that for Facebook's high-resolution settlement layer and the global human settlement population dataset. Both these datasets employ similar methods for mapping population, in that they identify settlements through satellite data and then spread census data across these settlements. Here you can see one of the downsides to the global human settlement population dataset, its coarse resolution. Whereas Facebook's high-resolution settlement layer dataset is able to identify individual buildings, and most of them are situated outside the floodplain, the global human settlement population dataset is able to capture this built-up area, but it's not resolved enough to accurately place it outside the floodplain. And what results is a higher flood exposure estimate. To finish with, I'm going to look at Rift Valley. These are the subbasins in Rift Valley, color-coded based on the exposure disagreement within each subbasin. The final subbasin I'm going to look at is this one in central Rift Valley, just north of Lake Abaya. In this basin, the global human settlement population datasets predicts far more exposure than the other two datasets. You can see on the map to the right here that the GHS POP dataset maps a settlement here that the other two don't. Now I did some investigation using Google Earth and I couldn't see a settlement of this size in the satellite imagery. The fact that these are global datasets means that they need to use automated methods to map population globally, and this will invariably lead to some errors cropping up. When using these datasets, I think it's important to double-check any results that seem odd to you. I know from personal experience from doing this analysis globally, I managed to pick up on a few errors for each of the datasets somewhere in the world. So that brings me to the end of my talk, and now I'll just summarize what I think the take-home messages should be. I hope I've shed some light on what different global datasets are available, both for mapping flood hazard and populations. And if you have any questions about using them and where to access them, please don't hesitate to contact either me or Mark Trigg. I've shown that the river representation of global flood models can have a significant effect on flood exposure estimates, and choosing the wrong model could leave a large proportion of the potentially exposed population unrepresented. So when using these models, it's important that you have an understanding of their limitations, and this understanding is reflected in the way you interpret the results. Similarly, the choice of population dataset used can have an equally significant effect on exposure estimates. Personally, I'd steer clear of using datasets that spread population across an area such as WorldPop. And I hope by highlighting some of the different reasons for exposure disagreement in basins in Ethiopia, you'll be able to look out for these if you ever use these datasets or similar ones in flood exposure studies. And finally, if you found the talk today interesting, we're about to submit the research as a paper, so hopefully look out for that in the future. Thanks for listening, and here's a slide of the datasets and papers I talked about earlier in the presentation.